Hello, today I want to show you how to use TRM to create an electro-thermal model and solution for a three-phase motor control board. As an example, I'm using this eval module from Texas Instruments. How does it look like? Looks like this. We do not treat the logic part, we only treat the power supply part. And we focus on the power stage, which is the MOSFETs and the shunts. The flow of current is assumed to be a DC approximation. We start at VBUT and follow the traces through the low and high side MOSFETs and the shunts, and then return the current from here to ground. In order to have as least as possible user input, we can make the transistors permeable for electric current, and we have the chance to add electric resistance, which is regulating the voltage drop and the power dissipation in the MOSFETs. So here we are using the RDS on value. We also use the known values for the ohms in the shunts. This is how the model looks like. The data come from the Altium files, which are available on the website or from Texas Instruments. It's not a problem to get this into the simulator. We see here in blue the pin for VBAT and in red the pin for ground. All these yellow components can be flooded with electric current so that the loop is closed. I'm switching to the transparent mode that we can see what happens here. Here's another transistor and inductance which have to be permeable for the electricity. What do we have to provide as input data? We need the definition of the currents, and the only current defined here is the current in the two pins. We assume 20 amps, and we have to define the electric resistance of these colored components. They are called Q, and the resistance is 3.3 milliohms, and the resistance of the shunts in green 5 milliohm. What do we get as a result? We get as a result, of course, a temperature map. But before I go into details, I will show the reason for the temperature. Of course, that's electric current. Let's have a look at the top layer current density. We start at VBUT. We flow through this MOSFET and the inductance, and then feed low and high side MOSFETs and shunts. We have electric current in all the layers. This is obviously a collection point, which then is connected to ground. This causes some sort of power density. It also creates a voltage drop or a potential distribution. We start here, plus 10 amp, which then has the highest value of the potential. We identify the voltage drop according to the local current and the definition of the resistance. This is also to check whether the nets are properly connected. And finally, we have the temperature distribution in all the components and the layers and the prepregs. The temperature rise isn't dramatic because this is a test board and has quite low ampere values. The delta T is about 20 degrees. What we see in the top layer is that there is a non-symmetric heating of the components. This one is the hottest because it's in between two other hots. This one is the coldest because it has only few neighbors. We also see that the capacitors have a non-symmetric heating. It's hotter on the right side and cooler on the other side. We also see that this capacitor has a higher temperature than this one and potentially a shorter lifetime. We can see the temperatures in any layer in the model. There's not only colors, we also have a report file. The report file shows by values a lot of data, electric fluxes and thermal fluxes and temperatures and so on, but also what's the total heat dissipation. The total heat dissipation is about 3 watts. 50% of 3 watts are created by the components and the other 50% by trace heating. Thank you for watching this video. If you want to have more information or if you want to run a test case with our help, then just send an email. Thank you very much for your attention.